Welcome to a lesson with Dr. Powell. Let's take a look at an optimization problem in calculus. Now, what is an optimization problem? We're looking for an optimal situation, an optimal result, like a maximum or a minimum to something. Let's, for instance, consider that we have a sphere, and maybe we'd like to um, put into the sphere. Maybe let's put in let's put in a pyramid with a square base that hits where the corners hit the edges of the sphere. Maybe we kind of come up here to the top of the sphere. And so we have a pyramid sitting in here. And suppose, there's different ways of putting this pyramid in. Really, it depends on the height that we chose to use. In particular, we could put the center of the sphere here, and the maximal volume of a pyramid would probably happen below the center of the sphere. So we could even call the distance from here to here y, and we could say, hey, the volume of the pyramid is going to depend on y. Now, if we go too low, then the pyramid would be really skinny and wouldn't have much volume. So the optimal thing will be somewhere in between here and here for y. So how do we figure that out? Well, we first need to come up with a formula for the volume in terms of y, and then we just want to find the maximum of that formula as a function. Now, how do we do that? Well, we've talked about graphing, and when we graph, we look for maximums or minimums. We do the same thing. We just treat it like a graphing problem, just looking for the maximum, and that's about all we do. So, but the biggest thing is first come up with a formula. Next, you treat it like graphing, find a maximum. But really, you only really need to go to the first derivative and do an analysis until you see the maximum popping up. So let's first do the hard part, which is coming up with that formula for that volume. Now, keep in mind, let's kind of look at some different pictures here in this case. We could think of slicing right down in the middle of the sphere, just looking at a circle. And then what we're going to see is we're going to see something like, in fact, maybe that's not the best thing to cut down the middle. Maybe we should cut down the diagonal. Maybe that would be better. Okay, so if we cut down the diagonal and kind of look at a crosscut this way diagonally, the nice thing about that is you actually see corners from here to here. And so if you turn the picture and look at your cut, you'd see this diagonal line appearing right here. Okay, looks nice. Next, okay, we have like this and this. This looks like a pretty good picture, but maybe we should lower it just so we can kind of see the idea that the center is higher than the actual flat place right here. So let's lower it down a little bit just for our picture's sake, so we can kind of get a feel for what's happening. All right, now how do we find the volume of a pyramid? Well, a pyramid is kind of like a three-dimensional triangle. Instead of 1/2 base times height, it's 1/3 base times height. The base would be the base of the square. We also need the height. Let's suppose this is y. Maybe we need a radius. Okay, of our sphere. Let's give ourselves a radius. Let's suppose it's 2. Okay, suppose that's 2. Then this would be, the height is going to end up being 2 plus y. Okay, we know that automatically. It's going to be the height, sorry. The height here. And just need to find the volume of that, or the area of that base. Well, we also know that this is a sphere. That's a radius 2. Oh my goodness. I can use the Pythagorean theorem here. This turns out to be the square root of 4 minus y squared on applying the Pythagorean theorem. Just this little bit right here. That's kind of nice. Actually, and what is that? That's actually in this picture. That's this diagonal from here to here. Just like that. Now, let's be somewhat clever. Let's look at that square base from that. And we have this distance here. Now, let's see, well, that's supposed to be like that. Okay. All right. Now notice that this turned and plopped right there actually equals a square. Also, this guy turned that way equals a square. Kind of fun idea. That tells me that the area is going to be obtained by just taking this right here, which is square root of 4 minus y squared, and squaring it to find this square and this doubling. And I guess another way we could have seen it is we could have doubled, let's see, well, if we doubled it all the way across, maybe that wouldn't have worked exactly. No, that wouldn't have worked, but it works here. In this particular case, if we take this, we square it, we get that square, and then we just have two of them. So basically the area of the base is 2 multiplied by 4 minus y squared. Okay, so that's equal to the base area. So if we take the area of the base and we multiply it to the height, so 2 times y plus, okay, well, yeah, y plus 2, I guess, 2 plus y, whatever. So that's the height, and the base, I just put the 2 out front, I guess. But so this is base, so base is right there and there, and this is the height. And then I multiply it by a third, so just put it right there. This is actually equal to the volume formula for the pyramid. Okay, so then let's go ahead and multiply this out, take a look at it, find maxes and mins. I'm going to ignore the 2/3 for now, just set it off to the side, because really it just kind of expands or stretches. But if I'm looking for a location where I might have a min or a max, I don't really need to use that with the derivative. So let's just multiply this out. Here we get 4y, and let's see, we get a minus y cubed, and we get a 8, and we get a minus 2y squared. 4y, 8, and minus y cubed. Okay, we get something like this. We take the derivative of this, and so we end up getting, for the derivative, maybe I'll do my work up here now. Now, the hardest part was finding that formula. Now, please don't get scared, because this is probably a pretty challenging example, but I put this up here because sometimes examples can be challenging and can involve some bit of thinking in order to figure this out. But it's not impossible, but yet we kind of think about the idea. Now, keep in mind, we in the problem itself, we wanted to maximize something. So that gave us a clue on what to find as a function of what. We wanted to find volume as the output of our function, because we wanted to maximize. So whatever you want to maximize, make that the output of the function for a quantity. Whatever you want to minimize, if you're minimizing something, do the same type of thing. So in this particular case, let's look at the derivative. And I can rewrite it, the order. See, negative 3y squared. And then we have minus 4y. And then we have plus 4. Okay, that looks like the derivative right there. Okay. All right, we take a look at that and we see if it's factorable. Let's see. Let's see here for a second. Get 12, and maybe let's see if we did. Yeah. Okay. So if we did something like 4 right there. So 2, 2, 3y. Let's see, we get minus and plus. I think that'll do us. Let's see, 2y and minus 6y is minus 4y. Oh, no, it didn't work because I have a plus 4 there. Oh, but then I have a -6. Okay, I gotta think about that. Okay, because I have a -3y sitting off right here. So I have to think about that. So make that a plus, then a minus. Let's see. See if that works. -3y. Yeah, and then I get a +4 and 2y minus. Yeah, okay, this works better. Okay, so I ended up getting that, and then from there, you notice. Why did I factor this? I factor this because I noticed that there's no domain problems. So the only thing that would make a critical point in analyzing this first derivative would be places that make this 0. So what makes it 0? Negative values I don't need. I'm just looking for the. In fact, y equals -2. You know what that is? That's way up here at the top, the pinnacle, and I don't want that. Over here, that'd be like a minimum. Over here, you can kind of see what we're going to get. It looks like it's going to be 2/3. So yeah, 2/3. Y equals 2/3 makes the first derivative equal to 0. So then you can do a sign analysis. Well, you can think of this as a quadratic if you did this point at -2 and has negative leading coefficient. It's gonna, if you multiply it out. So the first derivative looks something like this. Um, and you notice that you have plus or minus. So indeed, yes, you do get a maximum here at 2/3. So y equals 2/3 will produce the maximum volume pyramid. Now to find the actual maximum volume, you would plug 2/3 into the volume formula. Thanks for watching.